All right, so like I was saying, practice exam will be scheduled for next week in lab. So not this Tuesday, but the Tuesday the week after. Okay. So what we've got here is our practice exam. And it is a very straightforward exam. Or rather, very straightforward in the content that you need. And I've first page. So for each of the following questions, determine which data structure would be best suited to handle the scenario. So I'll list basically which of these we care about. Array list, linked list, stack queue, tree, priority queue. Now, priority queue, for those of you who you may have skipped over it because you didn't see any assignments, but there was a video on heaps right over here, or there were some videos on heaps over here. Those will briefly be talked about during the, those will be part of the exam. I probably will do Huffman encoding as part of the group exam because that's a more difficult topic, or rather more time intensive topic, I should say. It's not really, in my opinion, it's not too hard, but I've never had an issue with it. But I've seen that other students have, so maybe it just clicks better for me. So priority queue, and then set or map, those come from these concepts in the hash table videos. So these are those kind of concept questions. Tree relations and vocabulary. So in other words, just some questions we can answer here. And I will be going over this on next Monday. I will give all the answers for this next Monday. Draw an example of each of the following types of binary trees. Now on this exam, I don't actually have I don't think there's going to be many questions where I ask you to draw the answer or anything like that. Instead, what you'll do is that I'll have examples and stuff, or you'll choose things, or I'll tell you, okay, here's a tree, remove nodes from it such that you make it a full, complete, or perfect tree. Similarly over here, where I'm asking you to draw a tree that forms after you do this, that will be a multiple choice question where I give you, hey, here's a bunch of trees. Please select which one that would form. If in those cases, I would definitely recommend making sure you do your work on paper and then hand it in to a TA or upload it so that I can, if you get it wrong, I can give you partial credit, because the multiple choice can't tell you whether, or I can't see the partial credit there, but I want that. But I enjoy having an auto grader because that speeds up the process here. Similarly, a similar question will be there. Here's a tree. Show me the tree that results after I remove these nodes from it. So so as you can see here, a lot of conceptual questions, like show me that you know how adding works. Show me how removing things work, rather than coding over here. Show me pre-order versus post-order. Heap questions, same thing. So adding or removing nodes from a tree, adding or removing nodes from a heap, just like you would for a tree. Huffman coding, again, that's something I can go over in more detail. And then coding in general, I have some coding problems. I plan on having 3 coding problems, and I'm just deciding how to distribute them over the exam. So most likely it will be tree part 1 and hash map question on the solo exam, and on the group exam you'll have tree question part 2, where you'll use the answer from part 1 to do part 2 on the group exam. So size tree, cannot use this here. These are just recursive problems for practicing recursion. Is full. Let's see. I would say that the difficulty is definitely harder than the size tree method for the questions I'm going to ask, but it's definitely lower than the is full method. Okay, so the difficulty is in between these two questions for the tree. And then you're almost certainly going to have a question along accounting. And then the hash map questions all is pretty much always a counting question. Like, given a string, tell me how what the most common character is. Given a list of words, tell me what the most common word is. Given a list of numbers, tell me the most common number. Given given us this one over here, given a string, given us, a bunch of text, tell me which one the most common character is. So this kind of word counting question or string counting question or number counting question, that's going to be on the exam. Once you learn how to use maps like that, that's not too hard. If you want practice on more practice on this kind of question, go all the way back to lab 2 and work on the is permutation problem and use maps. If you use maps on the is permutation problem, you can get that done in O of n time. Same with the is unique function from lab 2. If you use sets or a map there, you can get that done in O of n time. Okay, and then analysis questions. Basically, what are collisions in hash tables? How are they handled? What is the worst case insertion and deletion algorithms for binary search tree Y? It will most likely be an analysis question on trees. All right. Again, these exams are generally a lot longer. Sorry, the practice exams are generally a lot longer and a lot more difficult than my actual exams. And when I say longer, they were longer than the 2-hour exams I used to give. So definitely much longer than what you'll be expected to do for the solo portion. Okay. So with that, I think it's time to talk about the upcoming lab, which is the Cheaters Hangman one. So give me a second. I'll be right back. I'm just need to make sure I swear I have that cable somewhere. Yeah, was there the entire time. Wow. Okay. Embarrassing. But, okay, that was weird. There we go. So, just curious, how many of you did Cheaters Hangman with Professor Fiore? I'm not sure if he still does that as an assignment or not. Because he used to do it as an assignment, and we both ended up doing it as an assignment, but I do it anyway. Cool. Didn't last semester, so this will be completely new for a lot of you. That's okay. It's one of those things that where we can just add the complexity. Okay. Okay. So for those of you who are not from for those of you who are not from the Anglosphere, Hangman is a very, very well-known game. It's very, very well-known. Let's go ahead and so the idea behind Hangman is that we have some number. We basically start with some number of letters. I'm going to be doing 4 because that's easy to process for us, just visually. We have a 4-letter word indicated by 4 blank spaces, and we want the person to guess in some number of guesses. Okay, and typically we draw, and as the person gets it wrong, we have like a gallows over here. Very morbid game. I don't understand why we have no problem teaching children to play this game. But as the person gets the guesses wrong, we draw the person, and when the person is drawn, they lose. This is a very typical computer science 1 kind of problem. we're not going to need to draw any of the people in this. We don't need to draw that. You can just report back how many guesses they have left, right? They have a certain number of wrong guesses they can make. They can make as many guesses as they want, but as soon as they get a certain number wrong, they lose. And so the idea here is that if my word is need, okay, if my hidden word is need, I chose a word at the beginning when we played the game. And if they choose A, I'll say, oh, A was an incorrect guess. They got it. That's too bad. You now have one less guess. Okay, and if they guess E, okay, then they got that right. And I fill them in and say, okay, the game state now becomes E blank EE blank. So I would say, the variable I would use to define where we are in the game is the game state. This is what the user sees as far as the hidden word is. And then then they can make their guesses, and eventually they'll get D'd. Is a D, they might guess D for D. They might guess H, get another one, -1 over there. So now it's -2 guesses. And then they guess N, and they've got need. Okay. So with that, so that is Hangman. So what is Cheater's Hangman? What is the assignment that we are doing? The assignment that we are doing, I'm trying to mix my drawing tools. That's never going to work well. Okay. The assignment we're doing is a lot more interesting. So the idea here is that we want to make a game of Hangman that will cheat, and its cheating will go undetected by the player. Right. So the idea here is that you can give this to you can show this to your unsuspecting roommate or something, and watch them get very frustrated as they cannot get the right answer. For those of you familiar with Wordle, okay, give me one sec. For those of you familiar with Wordle, there's this version of Wordle called Absurdle, which works on the exact same principles as you're about to see for a Hangman. So in fact, I'm going to show you Absurdle right now, which is another guessing game. Okay, so with Absurdle, basically it's kind of a mastermind game where you tell it you want to guess some words, and then it will tell you whether you got them all right or all wrong. Oh, sorry, it will tell you, and if you get some letters right, it will tell you either you got the letter right and it's in the wrong position, or you got the letter wrong. But it's the right letter, but it's in the wrong position. So if I say, let's see, let's see. I think vapid is a word that doesn't have any repeats here. So vapid, and look at that. I didn't get anything right. Let's see. Let's give it a random guess. It will help me here. Churn. Nope, that wasn't a good one either. Tawny. And here it's saying I finally get 1Y right. Now, if you've played Wordle before, you know that this is kind of weird getting this many guesses. Swarm, motto, score. Okay, so now we know this word has a Y and an E in it. I'm going to hit I'm going to undo some guesses. Okay, and I'm just going to hit give up. And it says elegy. Actually don't give up. Give up. Let's see. Jelly. What's going on here? Actually don't give up. And now I say give up. Elegy. What's going on here is that it's not actually, is that this game is cheating. The entire point of these games is that there's a hidden word. But here it says, well, I have the entire dictionary at my disposal and I can go through it really fast. You wouldn't be able to, so long as what the information I tell you is consistent with the answers that I told you in the past, I can cheat however I want and never actually have to fully commit to a word. Okay. So how does it do this? And so let's go back to our whiteboard, and I'm going to show you how we do this with a game of Hangman. and a much more limited dictionary. Okay. So again, let's go ahead and go back to 4-letter words. And I'm going to limit the 4-letter words I use. I should also mention that the dictionary file you have has all of the 4-letter words in it, all of them, because it's a spell checking dictionary. So just be aware, if you're playing with 4-letter words in your actual program, your computer might, start throwing expletives at you. So I highly recommend that you maybe work with 8-letter words instead. Just aware of that. And I'm not going to go through and try to remove all of those words from it, because if you know the Scunthorpe problem, that's kind of really hard. And that's a problem that has to do with difficulty in censoring certain usernames or certain web domains because of explicit substrings. It's a real problem. It comes from the name of a British town, Scunthorpe, where it had a problem going and registering their web address for their town because of an explicit substring. This is a real problem in computer science. I swear to, or possibly more in IT, but it's a real problem. So anyway, let's go ahead and condense our 4-letter word dictionary down. Say, let's pretend that these are the only 4-letter words we have. Took, tool, ball. Let's go with bang. Let's go with hats. And then we've got 3 with A. And let's see. Book. And look. Okay, that should be enough. Okay. So we've got a bunch of words here, and I chose my words a bit deliberately here. So let's go ahead and say we've got a the user guesses the letter E. Okay. There's no E's in any of these, so nothing is going to change. Why nothing is internally? We're going to be running. We'd run through the same algorithm that we're going to be running through, but what happens is, because there's it doesn't match any of these words, nothing changes. So what happens when a user guesses a letter? Well, as we'll see, is that we essentially play Hangman on every single possible word that we have left. So we play it on ball, play it on took, play it on tool, play it on bang, play it on hats, play it on book, play it on look. Now let's suppose the user guesses the letter. So we played all, nothing changes over here. So the user gets a -1 to their number of guesses that they have left. Now let's say they guess the next most common vowel, which is A. So what do? What we do at this point is that we run through Hangman on all of these and sort the answers by where they appear. I'm going to put in one more word because it's important. Let's do able, mainly because I want a letter with an A in it that's in a different location. Okay, so that should be good. So now let's go ahead and go through. And what we do is we play Hangman on each of these 8 words. So if the user was playing Hangman and we were playing real Hangman, and this was the word that was guessed, right? Ball. Then our output would be for that game would be blank B. Sorry, not blank B. Blank A blank blank. Right? So the words that are that would have this output are ball. If we because remember, the guess letter is A. Took. There's no A's in took, so the output for that game would be nothing. Same for tool. There's no A's in tool, so the board state would be this for tool. Now bang, that output for bang would be B would be blank A blank blank, because we would have to reveal where an A is. So I'll list it down over here. Hats, same thing. Let's see. Now book as well. Look. And then when we get to able, that has a different output. Even though it has an A, one A, just like the other one, it has that A in a different place. So the output for this game would be different. It would be A blank, blank, blank. Able. What we do is that we play a game of Hangman and all possible words in our word list. This is what we call these group of words. We call this our word list. We play a game on all possible words in the word list. And what we do is that we categorize our answers into word families. The word families is going to be a string, is going to be a variable. What kind of variable is it going to be? It is going to be, let's go ahead and actually write it down here. The word families is going to be a map. Map. Specifically, a map of string. That's what this is, a string. To a map of string to list of string. I figured since we're remote, I might as well spend the time going over this, and this would be the most useful use of your time. And I'll actually code up a bit of functions for you to get you started. So that's what all this is. So this thing over here, all of this, that's our map, word families. Where, and the key of this is the various outputs for all the games, and the values are a list of which words would have that output for the game. So now we have to make a choice. We have to decide which of these word families we're going to go with. What is the board state we're going to reveal? Are we going to go with this one, or this one? Are we going with which of these three? Because they're all mutually exclusive. If I take the top one, I can't come back later and tell them, oh, so sorry, the word I was thinking of was tool. And they're going to go like, whoa. It can't be tool because you revealed an A to me earlier, an A in the second position. There's no way we could have that. So these are all mutually exclusive choices. Now, what we suggest in our documentation is that the word list you stick with, the word list you use is the one that has, the word family you choose is the one with the biggest list, because that allows you to go the longest. That gives you the most choices. Make sense? The longest word list gives you the most choices for the future. Okay? So what we're going to do here is we are going to now, I'll go ahead. So now that we've decided that, I'm going to erase this, and I'm going to replace this list up here with only the words that were with a new list, which is this list over there. Word families is something that will get created and destroyed essentially every turn. Okay. So now that we've chosen our word family, which is blank, 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 we can go back up here and say, oh, I'm so sorry, -1. Now what we'll do is that we can let's say the user will guess the letter T. Again, what we do is we split this up into various word families. So we would have T blank, blank, blank over here. And we would have blank, 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 T blank, blank, because we'd have took comma, tool. And then over here, we'd have book and look. And honestly, which one will it choose? It will choose pretty much. Honestly, it depends on the algorithm. You don't necessarily have to code in a tiebreaker. It will pretty much randomly choose which one it wants to do. Let's assume though that it goes with the top one, right? Because all right, in which case we would go. Our word list would now be this. Seriously, when I say don't worry about coding in a tiebreaker, it's not going to really make too much of a difference. And we would reveal T. Oops. We would reveal T and then blank, blank, blank. And we wouldn't subtract the guess from them because they got it right. Let's go ahead and move to a different game for a second. Let's go ahead and move. Now, let's say that the user has one guess remaining. Okay. And this is the scenario I start the game with. This is what makes the game evil. Okay. Suppose we are over here, GOA, and our guesses are ETOA and G S and not T. It can't work. It can't work with T. So give me a second. The example won't work with T. So E, D. So let's say that the users made these guesses. Okay, and they have one guess left. Now, there are three words that I can think of off the top of my head that fit GOA blank, which is goat, goal, and goad. Right? And the idea here is that what's going to happen when you're at this position? If the user guesses T, then we would tell them it's goal. And if they guess L, we would tell them the word was actually goat if they lost. What you will never do is tell them it was goad, because that word should have already been eliminated. Okay? Make sense? So the game is complex, but it is also not necessarily it's complex in the fact that we've got to use these dictionaries, but it's not necessarily horrendously complex. I'm going to go ahead and code up a bit. Right. Yeah, let's go ahead and open up new project. Hangman. Create. And I'll share my screen for this. Yes, I know. Preempted you, some of you saying you aren't sharing your screen yet. There we go. So let's go ahead and create a new Java file. It's going to call it Hangman, right? And so I'm going to give you kind of a bit of an outline to help you get started. So the first thing I recommend you work on is something like this. 1 second. Public static. And then what we want to do is that we want to return a list of public static list of string. Public static list of string read or get, or rather, let's call it read word file, because that's what we're going to do. String file name. List of string words is equal to new array list. There we go. and return our words. So what you're going to do is over here is that you're going to read the file. Although actually what we don't want to do over here is that would just give us all the words. What we want to do is in fact not return this, but instead return a map of integer to list of string. Wait, why? Well, the idea here is that what we want to do at the beginning of the homework is that we want to sort all of our is that when we read the file, let's go ahead and sort it into a dictionary. So we can make a one with a key 3, and what we'd have is all the 3-letter words over here. So cat, dog, right? And then what we'd have over here as well is the list of 4-letter words like book and took and look, and all the 5-letter words like fives, you know, and fives and fires, things like that. So basically we can go ahead and sort that out. So this is a very good place to start because it gets you working with the map, which is what you want to do. So let's change it up. Words by size. New hash map. Okay. So that's what you're going to run that once when we start this file up. Okay. The next one we'll probably want to have is this whole word family thing. Public static map string list of strings, create word families. Now, what you need to do to create those word families, so remember, what does word families do? It creates a map, which I call word families. Families is equal to new hash map. And we will return that at the end. And that word families, the key is the board state, and the words are all the words that go along with that board state. In other words, what we do is that given a string, we ask ourselves, okay, we are going to go through the string and we're going to play a game of Hangman on this string. And we're going to do that for every single word that we've been given. So to play a game of Hangman on our strings, we need those strings. So we're going to take in list of string, the word list. So that is the current word list. And then over here, we're also going to take in a set of characters, which I'm going to call guessed letters. So those are all the letters that have been guessed so far. So what we do is that we take it, given all the words in the word list that we still have, and all the letters that have been guessed so far, we can figure out what the word family is. In fact, it might help if you create one more a helper method. You don't have to use this one. This is possibly the most optional method of it. The other ones are not really optional. Public static string get word family. Given a single word and and a set of characters called guest letters. Figure out which family it is in, string, or figure out what the family for this word should be. Right? It doesn't need to know whether or not the other families exist or what they were. It just says given a single word and the guest letters, what would the board state for this word look like? And that's its family. Now, for the last part of that is public static, and this one is also going to return a string. So what can be? It is get best family. And what that's going to do is, given this over here, given our word families from this function, we want to figure out which one is the one we're going to use for the next game, or the game. String best family. Family is equal to nothing because that I needed to compile right now. And that's all of the parts for what I would give you for that. Now, where should you play the game? You can play that in your in a main class or whatnot. Sorry, you can do the game in main. You can create a separate function for it for a game, but your game is essentially going to run like a while loop. Again, I highly recommend going through and just kind of actually coding it like in the order you would try to code it up, like the game would in the order the game would be played. Maybe not worry about guesses or end conditions quite yet. But first step, read the dictionary file, read all the words and separate them out by their size. Okay. So any questions on this one so far? Anyone? Okay. So yeah, this is again this is the last big assignment of the semester. Okay. The last big one. So once you've finished this one, for the last couple of weeks, you'll essentially be not home clear because you're still going to have some work, but they're not going to be nearly as arduous. It's not that we're done learning. It's that the things I'll be teaching you are a bit less programming intense and more theory intense and more process intense. So for instance, with the sorting homework, the coding is restricted to modifying the code, reading the code and figuring out, okay, what is a comparison and what an exchange is. Similarly for the graph problems, those are basically amount to, okay, given this file, sorry, given these libraries, how do I learn how to work with these libraries? Because what I want you to do, rather than building a data structure, I want you to use a library that has already been developed by somebody. Okay. Now, before I go over to helping people and or taking demos, do people want me to review heaps or Huffman encoding? Since I'm in a lecturing mood today. Or would you prefer me to just go to working with you and maybe save that for Wednesday? Not getting much input today. I get it. It's a very interesting. So I'm a big fan of learning different folklores for curses. You know, old proverbs like may you make your widow's husband very happy and rich. You know, and the one that keeps cropping up today is may you live in interesting times, because boy, strikes in multiple countries around the world, and then the whole water situation here. It's very interesting to have this this week, I guess. So hopefully everybody's okay with that whole water situation. But it is but I will be there on Wednesday, and we will go over this kind of stuff. As far as now is concerned, I am going to stay behind, obviously, because it's still class. And if you need help, I can separate us out into breakout rooms, and I can also, that's my priority, helping out students, or we could demo things. I'm at home, I have plenty of time, so no worries if you feel like you're going to be eating my time, which you won't be. And if you just feel like you want to head out for the day, that's fine too. All right, so I'm going to stop recording, and I'm going to split us up into breakout rooms.